Yeah, I'm going to post this on Classroom probably Tuesday. I won't be here on Monday. But let's go ahead and solve this. So, sodium hydroxide, that is NaOH. And you don't need the parentheses. Sulfuric acid, that is H2SO4. So what is the balanced equation? We have H2SO4 reacting with NaOH, and Na is going to get the SO4. SO4 has a 2 charge, so we need 2 sodium. And we get water. Balancing, we need 2 sodium over here, and then we need to double that. There you go, balanced equation. How many moles of sodium hydroxide were used in this reaction? So we were given this information. We were given 100 milliliters of NaOH, and we were given this conversion factor of 0.5 mole of NaOH per 1 liter of NaOH. And we know that 1 liter of NaOH is equal to 1,000 milliliters of NaOH. Dimensional analysis, you'll see that everything on this is dimensional analysis. ml and OH cancels out, and 1 liter, leaving us with moles. So 100 divided by 1,000 is 0.1. 0.1 times 0.5 is just 0.05 mole. How many moles of sulfuric acid was this? So, start with what we're given. We're given 0.0, which would be 5 right there, mole of NaOH. Again, dimensional analysis. We want conversion factor. And I want mole NaOH on the bottom. So I know we have a ratio of 2 mole of this to 1 mole of that. So I know 2 mole of NaOH is equivalent to 1 mole of sulfuric acid. So mole NaOH cancels out with mole NaOH, and that gives me 0.025 mole of sulfuric acid. You could have recognized all you need to do is divide by 2. You would have half as much sulfuric acid. But you will see I am very, very rigorous in doing homework problems to ensure I don't make a mistake. So what is the concentration of the sulfuric acid solution? So you take your number of moles of acid. That's what concentration is. Concentration is going to be in molarity. It's the most easiest to do. That's the only one you can do for this problem, and that's number of moles per liter. So it's in moles per liters. So my number of moles is 0.025 mole of sulfuric acid, and my number of liters is in the problem is 25 milliliters of solution. I've been putting just as H2SO4, but that's the solution. And I know that 1,000 milliliter H2SO4 solution is equal to 1 liter of H2SO4 solution. And milliliters of H2SO4 solution, and this cancel each other out, leaving us with moles of acid per liters of solution. So I get 1 molar, or 1 mole per liter. sulfuric acid, which is equal to 1 molar sulfuric acid. Moles per liter is molarity, and we can replace mole per liter with the symbol M, capital M. So barium is 2 plus, hydroxide is OH negative, so we need 2 hydroxides. Chloric, there's no hydro, so I know that this is going to use the 8 version, so I have HClO3. So I have HClO3 reacting with barium hydroxide, and barium is going to go get a chlorate. Chlorate has a -1 charge, so I need 2 of them, and that gives me water. So I have 2 chlorines, so I need to double that. 4 oxygen, so I need to have 4 oxygens over here. Balanced equation. For this problem, we can't solve for moles of part B yet, so do this one first. Chloric acid, you are given liters and molarity, so 25 milliliters of chloric acid. And I know that 8 molar means 8 moles of chloric acid per 1 liter of chloric acid. And I need to get rid of milliliters and liters, so I know that 1,000 milliliters of chloric acid is equal to 1 liter of chloric acid. Liters of chloric acid cancel out. Milliliters cancel out with milliliters right here, giving us just moles, is what we're looking for. So plugging that in the calculator, you get 0.2 mole of hydrochloric acid. Or not chloric acid. Now we can come back and do this problem. Given this information, I want a conversion factor of chloric acid to barium hydroxide. Well, this will tell me it. I know I have 2 mole of chloric acid for every 1 mole of barium hydroxide. Mole chloric acid cancel out, leaving us with moles of barium hydroxide. And that's equal to 0.1 mole of barium hydroxide. It's literally just dimensional analysis. You have your ratio of 2 to 1, and I always include units and go all the way out every single time, canceling them out until I get my answer. So what is the concentration for the barium hydroxide solution? So concentration, we'll do molarity, moles per liter. So let's do with what information we're started with. How many moles of barium hydroxide do we have? We have 0.1 moles of barium hydroxide. That's from this problem right here. And what's the volume? Volume is 125 right here. So all the way down, we have 125 milliliters of barium hydroxide. And now we just need to convert units until we get the answer we want. We know 1,000 milliliters of barium hydroxide is equal to 1 liter of barium hydroxide. And milliliters cancel out, and I'm left with moles per liters, which is molarity. So 0.8 molarity, or molar, barium hydroxide, and that's our answer. So moving on, calcium hydroxide and perchloric. So chlorate, so this is going to be chlorate, is chlorate, perchlorate, so that's ClO3, -1, and thus a per will turn this into ClO4. So that means we have HClO4 reacting with CaOH2, and this is literally the exact same thing as the previous problem. Nothing really changes, except for you put 4 on the oxygen and use calcium instead. So I need to double my chlorine and double my water. There you go, balanced equation. So how many moles do we have? So what do we know? Well, we know how many milliliters of calcium hydroxide we have, given to you in the problem, here and right here. And the 0.25 molar stands for 0.25 mole per 1 liter. And we need to cancel out milliliters and liters, so we get moles, and luckily we know 1,000 milliliters is equal to 1 liter. And by the way, even though I'm doing this the very long way, you could have used 0.05 liters to begin with. Some of these conversions you can do in your head. But again, whenever I do homework, I cross out everything and make sure everything, single possible thing's written out. That's 0.0125 moles of calcium hydroxide. How many moles of chloric acid do we have? We'll start with what we know. We know how many moles of calcium hydroxide we have. And we're going to use a conversion factor to go from moles this to moles that. And here's our conversion factor. For every 2 moles or molecules of this, we have 1 molecule of this. I put the 1 mole of this calcium hydroxide on bottom so that they cancel out. And that goes to 2 mole per chloric acid. So it's just 2 times that, which would be 0.025 mole of per chloric acid. Again, what is the volume? So let's start with what we know. We're only wanting to know the volume. So let's start with moles. Given the amount of moles, we need a conversion factor that will give us volume. So what conversion factor do we know? Well, I know molarity of it. I know that my molarity is 2 molar of butyric acid, so that means it's 2 mole of HClO4 to 1 liter of HClO4. That's my conversion factor. 2 molar means that. That means moles cancel out, and I'm in volume. How about like liters as volume? So I'm going to go ahead and do 1 liter to 1,000 milliliters conversion, because it makes the answer neater. So liters cancel out, and again, milliliters is a volume. So again, answer of 12.5 milliliters of perchloric acid. If you didn't do this last step, you would have gotten 0.0125 liters, and that's acceptable also, but this number is better. So again, I start with what I know and add a conversion factor that will get me into volume. Volume is liters. I went from mole to liters. That's the conversion factor given right there. Alright, stomach acid, also known as gastric acid, is mainly composed primarily of hydrochloric acid. Hydrochloric acid, hydro means it's going to be binary, so it's going to be a combination of H and Cl. H is +1, chlorine is -1, so it's 1 to 1. The molarity is 0.155 molar. Here I didn't abbreviate the word M. I actually wrote out it. It's molar, what the M stands for. So that means I have 0.155 moles per 1 liter of HCl. The normal volume is between 20 milliliters and 100 milliliters. Let's assume we have exactly 60 milliliters. So how many moles? Well, we have 60 milliliters of hydrochloric acid, and I have a conversion factor. So if you wanted to, you can go ahead and convert this into liters. So I know 1,000 milliliters per 1 liter. And to go from liters to moles, I use this conversion factor. 1 liter of HCl to 0.155 moles of HCl. That gives me moles. That's what I'm looking for. So our answer is 0.0093 moles of HCl. The active ingredient in tons is calcium carbonate. So we have calcium and we have carbonate. Carbonate is -1. Calcium is a +2, and that's -2. Carbonate is -2. Calcium, so that's 1 to 1, so that's CaCO3. And it has 750 grams of it. So write the balanced equation for HCl reacting with calcium carbonate. So calcium and the chlorine will react together, and we get hydrogen, which this is -2, so I need 2 hydrogen. So we get this equation. Balancing it, we need 2 hydrogen to counteract the 2 hydrogen here. We have 1 carbonate, 1 carbonate, 1 calcium, 1 calcium, 2 chlorine, 2 chlorine. You could have went with the full equation if you recognized that carbonic acid here is unstable and produces H2O and CO2. This will break apart into this. But that's irrelevant. You could have went with the first one. It doesn't change anything. So what is the molar mass of your calcium carbonate? So we're doing calcium molar mass, so that's the periodic table. We have 1 calcium, 1 carbon, 3 oxygen in calcium carbonate. So that'd be 40 times 1, 12.0107 times 1, and we have 15.9994 times 3. Add those all up, and we end up with 100.0869 grams per mole of calcium carbonate. Another conversion factor. How many grams do we need to neutralize the acid? So let's start with something we know. So we know how many moles. We have 0.0093 moles of HCl. And we can convert this by using this equation. We know that 2 moles of this, for every 2 moles of HCl, we need 1 mole of calcium carbonate. So moles cancel out. And now we need a conversion factor of moles to grams, which would be this. So 100.0869 grams of calcium carbonate to 1 mole of calcium carbonate. That cancels out, and I'm left with my answer, grams per calcium carbonate. So that times that divided by 2 gives you 0.4654 grams of calcium carbonate. Alright, how many tablets of Tums would thus neutralize your stomach cancer? Your stomach acid. So start with something you know and keep adding conversion factors until you get the answer. So I know how many grams, and I'm given milligrams per ton right here. So I'm going to go ahead and convert this into milligrams. 1 gram of calcium carbonate is equal to 1,000 milligrams of calcium carbonate. So grams cancel out. Milligrams, I have the conversion factor of 1 tons is equal to 758 milligrams. So 1 tons is equal to 750 milligrams of calcium carbonate. Milligrams calcium carbonate cancels out, and I'm left with tons, and that's what the answer was. So that is equal to 0.62053,878 tons. Which, honestly, I was surprised by, but now it makes sense after I got that. Did you think that taking a single tons would completely neutralize all your acid in your stomach? So if you take a tons, your stomach is no longer able to digest anything for a few hours. Note that your stomach is constantly pumping in acid acid is constantly being produced. So when you first take a tons, in a few minutes, eventually all the juices will mix together, and you would have no more hydrochloric acid. You would be left with actually a partial amount of tons. As you produce more acid, the acid is going to react with the leftover tons until it's all consumed. After about 3 or 4 hours, your body will have produced enough hydrochloric acid to completely destroy the tons, and it'll start generating acid again. So this problem, we're looking at another common acid, rolaid. So you're doing chemistry inside your stomach. Some of the foods or drinks you eat will react with calcium carbonate. So some companies add 2 chemicals in hopes that this chemical won't react with your food and make it work better. But the key thing is it has a combination. I'm not for sure if this is a mistake. It doesn't change the problem, however, because I said it was about a 5-to-1 ratio. If you actually take this number and that number, you see it's more of a 5.4-to-1 ratio. I don't know if I meant to do 625. I think I did. But regardless, I gave you 675. So magnesium hydroxide is MgOH2. And we're mixing with it, again, with stomach acid. So HCl. And we get magnesium chloride. Magnesium is going to react with chloride. And we get water. We need 2 Cl's, 2 chlorine, and 2 water. So that's the balanced equation. Again, we have 1 magnesium, 2 oxygen, and 2 hydrogen. So that's 24.305 plus 2 times 15.9994 plus 2 times 1.00794. And we get a result of a molar mass of 58.31968 grams per mole magnesium hydroxide. This problem right here is the most difficult one on the test homework. So when I solved it, I did a lot of work. Note, you will see in my official solution, I even went out and converted milligram. The ratio is 675 milligrams to 125 milligrams. I used the conversion factor grams to milligrams, only to end up that the ratio is still 675 to 125 grams grams. This should be common sense. The ratio of 775 milligrams to 125 milligrams is the same thing as 675 grams to 125 grams. Whenever I solve, and just if you want to come back and pause, there is my official solution. that I have written. But the key insight to this is that we have two molecules of HCl reacting with one molecule of this. In addition, we have two molecules of this reacting with one molecule of this. So the key insight to make this problem easier is that we have two acid molecules or moles reacting with one antacid molecule. Whether this antacid be magnesium hydroxide or calcium carbonate. So the question is, how many moles of antacid? And our antacid is some combination of magnesium with calcium carbonate. We have some combination of these two added together. So I'm going to let this be my sum. How many of these particles do I have? Well, I know I have 0.093 mole of hydrochloric acid. That is what I calculated right here. 0.0093 mole of hydrochloric acid. And I know the ratio is 2 to 1 and 2 to 1. So I know I have 2 mole of HCl to every 1 mole of MgOH plus CaCO3. Mole cancel out, and that gives me, I have 0.00465 mole of both calcium carbonate and MgOH2. We also know the ratio of calcium carbonate to magnesium hydroxide is 625, 675 to 125. And I'm going to go ahead and do grams so I don't do the waste of space I did. So I know my ratio is 675 grams of CaCO3 to 125 grams MgOH2. But I need to convert the moles. Well, I know 1 mole of magnesium hydroxide is equal to 58.31968 grams of magnesium hydroxide. That is this number right here. And on the previous problem, you have grams and moles right here. So that would give us, if you plug in 100.0869 grams of calcium carbonate to 1 mole of calcium carbonate. So grams calcium carbonate cancels out with grams calcium carbonate. Grams magnesium hydroxide cancels out with grams, so I'm left with mole to mole ratio. So I have a ratio of 3.1465284 mole of calcium carbonate to 1 mole of magnesium hydroxide. So I know also that the sum of these, the sum of the antacids, is equal, the sum of moles of antacids is equal to this number right here. So that means I have a ratio of this to that. So I have 3.146524 times some X amount plus X moles of this, and that is equal to 0.00465 moles. Solving for X, that is equal to 4.146 0.06284x equal to 0.00465 mole, and my x is equal to 0.0011242 mole of magnesium hydroxide, because my x right here is how many moles of magnesium hydroxide. My x right here, this would be my total amount of calcium carbonate. So to get calcium carbonate, so this is my calcium carbonate, this is my magnesium hydroxide. So if I multiply my x by this number, so 3.1465284 times my x, which this is my x, I would get that I have 0.35165 grams of calcium carbonate. So this is how many grams I have, and this is how many moles I have. And this is how many moles of that I have. So I can convert these two numbers into grams. So using grams per mole, I can convert this number, which would be 0.06. And I just realized, sorry, I'm getting off. This will be 0.003528858 mole of calcium carbonate. So multiplying this number by 58 would get me 0.0654 grams of magnesium hydroxide. Multiplying this number by the conversion factor of 100 grams per mole, I would get 0.353165 grams of calcium carbonate. And if I add them together, the sum is 0.418565 grams. And the sum of them is our Rolade. So I have this many grams of Rolade. And then, to convert grams of Rolade to whole number of Rolade, you should recognize that a single Rolade, I'll just write over here, a single Rolade has a total weight of 675 milligrams plus the 125 milligrams, giving you a total of 800 milligrams. And 800 milligrams is 0.8 grams. So, let's see if I can put this in right here. I have 0.418565 grams of Rolade, and I know that one Rolade is equal to 0.8 grams. Doing this combination, you get an answer of 0.5232, rounding, actually I want 4375 Rolade. Again, this one was the most hardest to do. It's because you have to realize you have two antacids and you have to keep track of it. This would have been a way difficult, more problem if the ratio wasn't two acid molecules for one of these and one of these. Does that make sense? So that was the only really difficult problem to do. So here we have phosphate. So phosphate is PO4 -3, and acid is H+. So I have H3PO4 and barium hydroxide. So barium is going to come over here. Barium is a +2. So we get 3 of those and 2 of these. Alright, so I need 3 over here, and I need 2 over here, which means to balance it, I need 6 water. How many moles of phosphoric acid do we have? Well, I tell you that we are making a 200 milliliter solution. So, we'll start with, or let's see. No, you have a 200 milliliter solution of this acid. So 200 milliliters of phosphoric acid. And we know that 2 moles of this is equal to 3 moles of this in the equation. So 2 moles of phosphoric acid for every 3 moles of barium hydroxide. Moles cancel out. No, never mind. I'm sorry. This is wrong. That doesn't cancel out. So I did the wrong thing, so let's try again. Why dimensional analysis is so powerful. I need to cancel out milliliters. So I'm going to use this ratio, 0.5 mole of acid per 1 liter. And I need to cancel out milliliters, so I know 1,000 milliliters of acid to 1 liter of acid. So liter of acid cancels out, and milliliters of acid cancel out there. And that gives me 0.1 mole, as mole is my only unit left. So how many moles of barium hydroxide? So start with what we know. We know this ratio, 0.1 mole of H3PO4 phosphoric acid. I know this is where we know our ratio. We know the ratio is 2 mole of acid to 3 mole of base. This mole cancels out this mole, giving us 0.15 mole of barium hydroxide. How many grams do we need? 0.15 mole of barium hydroxide. Here we're going to have to use the molar mass. So 1 barium, 2 oxygen, 2 hydrogen. That's a ratio of 171.34168 grams of barium hydroxide to 1 mole of barium hydroxide. That's molar mass. That gives you 25.701252 grams of barium hydroxide. Explain how you would make a 2 milliliter solution. So, one, you cannot mix a acid, strong acid, or you can't add water to a strong acid or base. You always start out with having a lot of water and then diluting it. So personally, what I would do is I know I want to get to 250 milliliters. So I'd start out by measuring about 100. So measure between 100 milliliters to 150 milliliters of water. Slowly, and the key word is very slowly and carefully, stir in the 25.7 grams of barium hydroxide. Well, first you need to measure out as precisely as possible. As precisely as possible. This. So you measure out this. Slowly stir in until all dissolved. If needed, let it cool off. You do not want it to start boiling, as this is very exothermic. And then add enough water to reach our 200 millimeter mark. But we always add our acid and base to water, never water to acid or base. And what is the final molarity? Molarity is moles per liter. So how many moles of barium hydroxide do we have? We have 225.71252 grams. So don't use that. We use moles. So we have 0.15 mole of barium hydroxide. And that's per, how many liters or volume do we have? Well, we just made 200 milliliters of it. So we need liters. So we have to do 1,000 milliliters to 1 liter of barium hydroxide. Milliliters cancel out, leaving us liters. Moles per liter is our molarity. So we get 0.75 molar barium hydroxide. What is the molarity of a bottle of vinegar, given that the bottle says it has 5% acidity? Acidity, the percentage states that it's the mass in grams of the solute, the vinegar, per 100 milliliters of solution. So that means 5% of 100 milliliters is our vinegar in grams. So 0.05, that's 5%, times 100 milliliters gives us 5 grams. And this is 5 grams of acid, 100 milliliters of acid. 5 divided by 100 is 5%. But we want molarity, so we need to convert grams into moles. Doing the molar mass of acetic acid is 60.05196 grams per 1 mole. So that gets rid of grams. But we want our answer in terms of liters, so we need to cancel out the liters. So milliliters to 1 liter. So milliliters cancel out. And doing this, you would end up with 0.82161786 moles per liter. Moles per liter is molarity. So that's how much molarity we have. This problem, household ammonia, this particular one has a density of that, and it's about 10%. And we pour 100 milliliters of it in a beaker. So how much do we have in the beaker? Well, we know it's weight per weight. So, start with 100 milliliters of NH3. And I also, and personally in my deal, I even went ahead and did 1 cubic centimeter per 1 milliliter is equal to cancel out milliliters. But you should also know, again, I go fully out whenever I solve things, should know grams per cubic centimeter is the same thing as grams per milliliter. I've said that multiple times. So that's 0.957 grams per 1 milliliter. And that gives me my grams right there. So milliliters cancel out, and I'm running out of time. I'm trying to hurry up. That's 95.7 grams of NH3 solution. So this is how much the total solution has. This was for the solution. How many grams of pure ammonium do we have? Well, I know 10%. This is grams per gram. 10% of it, 10% of this is how much we have. So 0.01 times 95.7 grams tells me I have 9.57 grams of pure NH3. I really thought I could finish this in one period. But the rest is really simple. So how'd you do on it? What was giving you the most hardest trouble? Yeah, this one is the most, that one with the Rolade is the most hardest. Yeah. I probably won't grade that one. I'm probably going to ignore that one because of how difficult it was. But it was solvable, and it wasn't that difficult. You just have to really think about it. Alright. I'm going to finish recording this, and I'll post this sometime next week. Alright. So how many grams of pure ammonium do we have? Well, we know 10% of the ratio is, so 10%, so weight per weight is our mass of solute divided by mass of solution. That means 9.57 grams, or pure, divided by the total mass, the solution, equals 10%. And that should be 0.1. Sorry, I was trying to rush. Another way of writing this is X percentage, so X amount of the total solution. The total solution mass is 95.7 grams, equal to 10%. And 10%, written mathematically, is 0.01. So cross multiply, you see X is equal to 0.1, and I keep doing 1% and not 10%. 0.1 times 95.7 grams gives you 9.57 grams. So what is the molar mass? Molar mass is the periodic table. We have 1 nitrogen, and we have 3 hydrogen. Adding that together, the molar mass is 17.03056 grams per mole. How many moles of pure ammonia is there? Well, we know how many grams we have. We calculated that in part B. And we know the molar mass conversion, which is 17.03056 grams per 1 mole. So grams cancel out, giving us moles. So that's 0.56193 mole of NH3. And what is our molarity of the final solution? Molarity is, of course, moles per liter. So we start with our moles. 0.561931 moles of NH3. And we use our conversion factor here. It is 17.03056 grams of NH3 per 1 mole of NH3. Moles cancel out, giving us, dang it. Again, once we see that we're making a mistake, dimensional analysis helps. Sorry, the bell system is distracting me. 0.561931 mole per NH3. We're trying to get moles per liter, so we need to take our moles of NH3 and divide by our volume of NH3. Or volume we poured out 100 milliliters. So we're going to divide this by 100 milliliters. This is moles per volume, but molarity is specifically moles per liter. So we need to convert milliliters into liters. So milliliters cancel out. And now I'm left with moles per liter. So that would be 5.61931 moles per liter, which is molarity. And that's our answer. Alright. Number 8. You fill a beaker with 50 milliliters of water and slowly stir in 21.2 grams of potassium hydroxide. After ensuring all the base is dissolved, you add enough water to get the final solution to 100 milliliters. So your final solution is 100 milliliters. In total, you use 90 milliliters of distilled water. And distilled water has a density of exactly 1 gram per mole, or a milliliter. So how many moles of potassium hydroxide did you use? So we know the grams, and we can convert grams into moles by using molar mass. So 21.2 grams of potassium hydroxide. And that's 1 potassium, 1 oxygen, 1 hydrogen. That all adds up to 52.11694 grams of potassium hydroxide to 1 mole of potassium hydroxide. So grams cancel out with grams, giving us moles, and that's what we're looking for. So we have 0.4067775 mole of potassium hydroxide. What is the concentration of our final solution in terms of molarity? That's mole per liter. So here's our moles, 0.406775 moles of potassium hydroxide, and we're putting it in 100 milliliters. Our final solution is, so we have 100 milliliters of KOH solution. We need to do it in liters for molarity, so that's 1,000 milliliters of KOH solution is equal to 1 liter of KOH solution. So that cancels out with that. So I get moles per liter, moles of base per liter of solution, or mole of solute per liter of solution. So I get 4.0677775 molarity, moles per liter, potassium hydroxide. What is the concentration of a final solution in terms of percent by weight? We're using weight per volume. Again, turning back over, weight per volume is mass of solute in grams per volume of solution in milliliters. So I need to get an answer that's in terms of grams per milliliter. So I already know grams. My grams is 21.2 grams of potassium hydroxide. And I know my milliliters. My final solution is 100 milliliters. So I'm already in grams per milliliters. So that's just equal to 0.212 grams per milliliter, and are equivalently 21.2% KOH by weight per volume. And that's your answer. How many grams of water did you use? Well, it says we used 90 milliliters of water, and water has a density of 1 gram per 1 milliliter. So that's equal to 90 grams of water. What is the concentration of the final solution in terms of weight, where it's weight by weight? Our gram solute per grams solution. Well, my grams of solution, I used 90 grams of water and 21.2 grams of KOH. So my total grams of solution is 111.2 grams. And I used 21.2 grams of KOH, my solute. And that's equal to 0.1906475. Expressed as a percentage, that's 19.06475% KOH when using weight per weight. What is the volume of potassium hydroxide used? Well, I know the final solution. So the solution, and a solution is made up of two parts. The solution is your solute plus your solvent. So my solution has a total volume of 100 milliliters. And I used my solvent with water. I used 90 milliliters of water. And if I subtract these two, I get my solute, or my potassium chloride, potassium hydroxide, which would be 10 milliliters. So my answer is 10 milliliters of KOH. So I have a 100 milliliter solution, 90 milliliters of water. That means 10 milliliters has to be potassium hydroxide. So what is the concentration of the final solution in terms of volume per volume? So again, this is volume solute per volume of solution. My total solution is 100 milliliters. So this is your solution. And my solute was my 10 milliliters of potassium hydroxide. So that is 0.1 expressed as a percentage. That is 10%. And this is by volume per volume. I did this problem was meant to show you that you can express the concentration in multiple ways, and you have to be very careful, especially when dealing with percentages. This is why molarity is the preferred concentration to use in chemistry. This tells you exactly what you need to do chemistry with. Look at how different all three of these values are when done as a percentage. And oftentimes you'll get a bottle and it'll tell you what percentage it is, but don't tell you what type of percentage. And look, if you assumed it was weight per weight, that 10% volume by volume is equivalent to almost 20% weight per volume or weight per weight. So if you grab 10% and assume we're thinking that this was weight per weight, and it was really volume per volume, your solution is actually twice as strong than what you were thinking it of. Lastly, density. Density is equal to mass per volume, or mass. Potassium hydroxide was 21.2 grams. And it was contained in 10 milliliters. So we have a density of 2.12 grams per milliliter. The density of pure potassium hydroxide. Last problem. We have 18 molar sulfuric acid supply in the lab. Suppose we put 100 milliliters of this into a small beaker. We also have a large supply of distilled water. This isn't true. I'm going to have to make some. And I really don't look forward to making it. It's a really long and tedious process, but we need it for next week. So that's what I plan on doing the weekend. How many moles of sulfuric acid are in 100 milliliters? So we start with 100 milliliters of sulfuric acid. We have a conversion factor here that is 18 moles of sulfuric acid per 1 liter of sulfuric acid. Liters and milliliters don't cancel out, so we need 1 liter to 1,000 milliliters. So liters cancel out liters, milliliters cancel out milliliters. So we get 1.8 mole of sulfuric acid. How much distilled water is needed to dilute this to 1 molar solution? So a 1 molar solution means a 1 molar means you have 1 mole of sulfuric acid to 1 liter of sulfuric acid. Or equivalently, you just have a 1-to-1 ratio. So you could have 1.8 moles of sulfuric acid and 1.8 liters of sulfuric acid. And you know, to convert between liters and milliliters, you simply multiply that by 1,000. So what you need to do is put 1.8 moles of sulfuric acid into 1,800 milliliters solution. We currently have 1.8 mole in 100 milliliters, and that gave us the 18 molar. We want 1.8 mole and 1,800 milliliters to give us a 1 molar solution. So how much water do you need to add to go from 100 milliliters to 1,800 milliliters? You need 1,700 milliliters of distilled water. And lastly, describe the procedure. You can do 2 things. The most simplest thing is to measure out 1,700 milliliters of distilled water and very, very slowly, and the key word is slowly, pour in pure H2O, pour in very slowly your 100 milliliters of sulfuric acid. You want to stir it up, and you want to make sure this stays well below the boiling point. This is going to heat up very, very fast. If you pour it in all at once, this will immediately boil, and you will have an acid fog all in the room, and you will severely hurt yourself and anyone else in the room. So you very slowly pour this in. Very complicated. If you have 2 liquids of different volumes, but different densities. So if you have 100 milliliters at some crazy density, so let's say this is 5 grams per milliliter, and we mix it with 200 milliliters of something that's 1 gram per milliliter, you expect this to be exactly 300 milliliters. In reality, that's not the case. I mean, this right here, definitely this solution right here, the key point is you take the water and slowly put in the acid. This will work. The reason why in reality this isn't exactly true is, imagine you have the molecules as being giant big balls or spheres, and they're all packed in a container. And imagine you then put in little tiny spheres. These little tiny spheres can actually fit in the gaps. And what happens when you mix 2 different liquids of different densities, is you can wind up with a solution that is slightly less volume. So you would not need to worry about this, as and this would be probably like 299 milliliters when added together like that. It would be a small percentage off. The fully accurate method that doesn't even account for or doesn't need this is let's measure out 1,500 milliliters. We slowly measure out 115 milliliters of distilled water. Slowly and carefully, ensuring temperature. You probably want to put ice too. Put this on ice blocks. Slowly and carefully ensuring temperature doesn't get close to boiling. Add the acid. Add 100 milliliters of acid. Then you'll get somewhere around 116 milliliters. And then what you'll do after that, so we're now at around 1600 milliliters. You then add water. Again, add water slowly. You should never add water to an acid, but this is diluted. We've diluted our acids to make it safe. Add water slowly and carefully. Until you reach exactly 1,800 milliliters. And that's how you mix them together. This method is more precise, as it does take into the account of the fact that the smaller molecules can squeeze in between the gaps. But really on this size right here, since this is so much smaller than this, it doesn't matter. 117 milliliters plus 100 milliliters is going to be so close to 1,800 milliliters that it really does not matter. So you could have measured out this carefully. The reason why you would prefer this over this less precise method of mixing to where you get only approximately 18 is because sometimes you can't measure in a beaker precisely enough. You need to put it in a graduated cylinder, then transfer it over. So you do like a graduated cylinder that can measure to 500 milliliters precisely. And then you have a large beaker over here. You keep dumping this over until you can precisely get 1,700 milliliters. If you use a big beater that can hold 1.5 liters of liquid, chances are you're not going to be able to read this precisely enough. So if you put this in a large beaker, you're probably going to be off anyway. You probably will get somewhere between 1650 milliliters to 1750 milliliters. You won't be able to read this precise enough. That's why usually you measure out this large volume first. So even when mixing it in, this might in the lab be more precise in this way, unless you have a very precise way of measuring this, which for high school lab we do not. But that was the homework. Besides that one problem that I'm probably not going to take points off for, as it was very involved, the one calculating the number of Rolaids needed to neutralize. Everything else was just conversion factors. And you notice I made bunches of mistakes. I started solving for the wrong thing. But as long as you keep track. So like for example here, I started milliliters and I did mole to mole. That was not the right conversion. I need my answer to be in moles. So I canceled out milliliters, I canceled out liters. It's all dimensional analysis until you get your result. You really just pick some random numbers and start working with it until you get your final result. And of course, you need to be able to get the balanced equation correctly.